If the ground is a mystery, your design is a guess. Today I'm going to show you how to read a geotechnical report and when you must order one. I'll show you how you can save hundreds of thousands of dollars on footings, and by the end of this video I'll give you a word-for-word script to ask your geotech the exact parameters you need. So let's head to our second brain. Head to Footings and Geotech, then go to Geotechnical Reports, expand, and then head to Geotechnical Reports. Alright, and before we get started, just bear in mind that a $600 soil test is not a geotechnical report. Keep that in mind. I'm sorry to let you down, but you get what you pay for. In Australia, we call them a site classification report, which is usually a Class B with 100 kPa bearing capacity. Don't get me wrong, if you're designing small structures, lightweight residential jobs, a $600 site classification report will work fine, because for these types of structures, any soil with a bearing capacity of 50 kPa will do the job. And we talked about that in the previous lesson on site classification reports, and we also talked about some common footing systems that can be used for each site classification. But today we're going to talk about a full geotechnical report. First things first, what is a geotechnical report? In simple terms, it's a document prepared by a geotechnical engineer that describes the ground conditions, and it also gives you design recommendations for foundations, for slabs, footings, retaining walls, basement walls. So the geotech is going to give you all the parameters that you as a structural engineer require to design a certain structure. Now, when do you have to order a geotechnical report? For my mates in Australia, I would say really any time that a structure is not defined by AS 2870 and AS 1684, then I would order a full geotechnical report. But generally, if you are designing structures with heavy loads in the hundreds or thousands of kilonewtons, if you're designing buildings with basement walls, structures with high lateral loads, wind-sensitive structure, or earth-governed structures, retaining walls for large developments, you should order a full geotechnical report with all the K values, with the angle of friction, unit weight of the soil. This is a site development in Brisbane, for example. What happens is you've got a bunch of investors, the developers, and they buy a big block of land and they start subdividing this block of land to build several houses in that area. And to do that, they need to cut and fill the site to make all the pads level so that they can build the house on a leveled pad, on a flat surface. And to do that, they need the structural engineer to design all the retaining walls to retain the fill or to retain the cut. You might also require a global stability report for all your retaining works. I would also order a geotechnical report for sloping sides, near batters, or embankments. For this type of situation, you want to have a clear picture of the soil profile. You don't want your structure to slide down the hill. You might also have to order a global stability report. And some real life examples of these structures would probably be like your multi-story buildings, long span sheds, or even high-end architectural houses. Just a quick story before I keep going. I was chatting with a friend of mine. His name is Andrew, and he's a structural engineer in Sydney. And he had just had one of those cheap now, expensive later moments. So what happened was the architect commissioned a geotechnical engineer, and the geotech went to the site, did all the tests, did DCP down to rock. The report came back with a 600 kPa bearing capacity for that rock. Now, this house that he was designing was huge, right? It probably looked very similar to this one on the photo. It's a high-end architectural house, reinforced concrete, open plans, massive spans, huge loads. It's like one of those beachfront $10 million houses that you see in Sydney. So pressure is 600 kPa. And in area, let's say we have a board pier with 900 millimeters diameter. So that's a pretty beefed up board pier, 900 millimeters. That looks really good. So the area of a 900 millimeters diameter pile is PD squared divided by 4. And then you multiply that by 600, you've got that the end bearing capacity of this pile is 380 kilonewtons. If you need more capacity out of that pile, if you need more than 380 kilonewtons, you will have to utilize the pile skin friction, which means you will have to socket the pile into rock. And drilling rock is very expensive and very laborious. So what Andrew did was to contact the client and ask them to engage another geotechnical engineer. Now the second geotech report cost the client $7,000, an extra $7,000. However, the geotechnical report came back with a bearing capacity of 2000 kPa. So it went from 600 kPa to 2000 kPa. If you do the maths again, for a 2000 kPa times the area of that 900 millimeters diameter bored pier works out to be 1272 kilonewtons. So now we have a capacity that is 4 times greater than we could achieve with the first geotechnical report. So overnight, they had shorter piles and they didn't have to drill into rock. The client had an extra cost for the geotechnical report of $7,000, right? $7,000, but it saved $80,000 on construction costs. So I'm just telling you this story so you can appreciate the power of having a really good geotechnical report, a really good engaging a decent geotechnical engineer. And the opposite could also happen. In fact, it happened to me a lot. The geotechnical engineer goes on site and then they start doing the tests. They hit a boulder, for example, and then the geotechnical report comes back with rock. The structural engineer designed the footings for rock, but then when the builder is on site drilling the ground, they can't find any rock. So they drill 5-6 meters down and can't find any rock, and then they have to call you and say, hey, we can't find any rock, and you asked us to found the footing on rock. So you have to redesign that footing. It's a time wasted. The builder has to stop the works on site as well. Waste time, waste money. Always good to have a proper geotechnical report, that's for sure. Now, quite important question now is, how do you communicate with your geotechnical engineer? In simple terms, you ask your geotechnical engineer for footing recommendations and all the design parameters that you require to structurally design the footings. We're talking about things like allowable bearing capacity for high-level footings, like pad footings, strip footings. And allowable bearing capacity is the ultimate bearing capacity divided by a factor of safety, which is usually 3. And that takes into account the strength and serviceability. So when the geotech gives you the allowable bearing capacity, the settlement of that footing is already factored in for the allowable bearing capacity. So you have the failure and the settlement. And because there is a factor of safety applied to allowable bearing capacity, that's why we structural engineers size pad footings, strip footings for serviceability loads and not ultimate loads. So the allowable bearing pressure takes into account mainly 2 things: the failure load and the maximum load that the footing can take without excessive settlement. And why this is important for you as a structural engineer? Because different sizes of pad footings will result in different levels of settlement. A large pad footing has a larger bulb of pressure. So the larger the footing, the larger the settlement. We're going to see that in a second when we start reading the geotechnical report. But when your geotech gives you a table with footing sizes and their respective allowable bearing pressures, they have calculated the bearing pressures for the settlement of that specific size of footing. So for example, if you've been given a 200 kPa bearing capacity for a 2 meters by 2 meters pad footing, that does not mean you can use the same 200 kPa bearing capacity for a pad footing that's 5 meters by 5 meters, because the settlement changes with footing size. I'm gonna leave the link of an article written by Alex, a geotechnical engineer in Perth, and it explains very well what I'm talking about. It's called Notes on Allowable Bearing Pressure. Alex also provided the geotechnical report that we're going to go through today. So shout out to Alex, give him a follow on LinkedIn. What else can we ask our friends, geotechnical engineers? We can ask for deep foundation parameters. If you're designing piles, you would require both vertical and lateral design parameters, skin friction, base bearing, shear strength, some pile recommendations if we should use board piers, driven piles, screw piles, CFA, advice on site-specific conditions like fill, groundwater. You might want to discuss with them and with the civil engineer as well the most cost-effective way to support the building. Maybe instead of using piles, the geotech and the civil engineer might recommend some ground improvements and high-level footings. We would also require the soil reactivity class and the expected vertical movement. This section of the report would really apply to countries like Australia, UK, South Africa, China, I think India, and some other countries as well, where there is a clay soil that shrink and swell with the seasonal moisture change. So in the dry season, the soil shrinks, and in the wet season, the soil expands. If you look at some clay soils in dry season, you can see that they even form cracks. And then when it's wet season, that cracks fill with water and the clay expands. And it doesn't expand only sideways, it also expands up and down. And as a result, the slabs and footings will also move. So that's why it's important in these countries that we have a soil reactivity classification. Some people call it expansive clay. We call it reactive clay. And finally, I've got a brief here from a structural engineer to a geotechnical engineer. This brief has pretty much every information that you need as a structural engineer, and you can adapt that to your specific scenario. You know, maybe you don't have retaining walls in your project, so you'd probably delete all the pressure coefficients, the angle of internal friction, or maybe you don't have, I don't know, roads or pavement, so you don't need the pavement design parameters with CBR. It's a complete brief, takes whatever suits your specific project. Next, we're going to go through a geotechnical report together. It might sound simple to you, but I'm going to show you how you can really extract value from a geotechnical report. All right, let's go through the report. Shout out to PTG engineers and Alex again. First things we're going to look at is the site background information. And then we have a desktop study, which is basically a review of the existing information about the site or that region. It's pretty much a geological survey of the region where the site is located. As the name suggests, it's a desktop study, so it's not an actual site investigation. But I would assume that you might be able to draw some correlations between this survey and the actual site investigation. The next section is the field investigation, which is the field work method that the geotech used to carry out the site investigation. And in this case, they've done 12 CPTs, and CPT stands for cone penetrometer tests. And as you can see on this table, they went as deep as 4.5 meters below the ground level. Sometimes in this section, you will find, instead of CPT, SPT, which is a standard penetration test, and it's also widely used in Australia and around the world as well. So in this section, you would probably have a table with borehole 1, borehole 2, borehole 3 for the SPT tests. Or sometimes you might have both of them. For certain projects, they might do CPTs and SPTs as well. And then we have the field work results. And this section will be the results from the CPT or the SPT or whatever method the geotech chose to use. And by looking at this table, you can tell that the geotech found a 1 meter of fill over a dense to very dense sand. From the ground surface level down to 1 meter deep, it's going to be fill. And then after 1 meter, it's going to be dense to very dense sand. And they did not find the base of the sand. So possibly the sandy soil continues down deeper than 4.5 meters. And these are the parameters that a CPT test would provide, which is the bulk unit weight, and then you've got the drained cohesion, effective friction angle, and then the Young's modulus. Also, when we have fill like this, we would consider it as uncontrolled fill. That means it's not good to use as a base for the footings. unless there is some documentation to confirm that the field was controlled and placed under the supervision of a geotechnical engineer. You can also read here that no groundwater was encountered, but if there was a water table, the geotechnical report would provide you with recommendations on how to deal with that water. Depending on the water level, that would influence the choice of footings. For example, you might not want to use board piers because as you start drilling the ground, the water will keep filling the holes. And also, if the building you're designing has a basement, that's very important because you want to know if the groundwater is above or below the basement. So let's keep going. Oh, you might also use these values to design piles for lateral loads. So the next section is the shallow foundations. Shallow foundations is your high-level footings, which could be a strip footing or a pad footing. For example, for a pad footing 3 meters by 3 meters sitting on sand, which would be at 1 meter deep, we would get a allowable bearing pressure of 275 kPa. And that's the table that I was talking about when I said that you shouldn't use the same allowable bearing pressure for different dimensions of footings. As I said, different size of footings will have different settlements. Therefore, do not use footings with dimensions larger than the ones given on this table without double checking with your geotechnical engineer. Next section is for the deep foundations. Now we're talking about piles, and we've given a shaft capacity of 10 kPa and a base capacity of 3 MPa. And notice that this is ultimate capacity, so there's no safety factors applied to these values. And that's because allowable bearing capacity would vary depending on the type of pile that you're using. For example, you might get a better shaft capacity if you're using driven piles instead of bored piles in sand. You probably don't want to use bored piers anyway in sandy soil because the soil will keep collapsing, will keep caving in as you drill. I'll leave a link of a video on piles that I've done on YouTube in the description below. You can go there and watch that video after you finish this one. I talk all things pile in there. Depending on the project, the geotech will provide an allowable bearing capacity for a specific type of pile that they recommended. For example, if they recommended, let's say, board piers, you would get a allowable shaft adhesion and also the allowable end bearing pressure for the pier. And also remember that skin friction to a depth of 1.5 times the pile diameter below the ground surface must be ignored. And that comes from the Australian Piling Code, AS 2159. So if this is your board pier, the first 1.5 meters of skin friction has to be ignored. So you only use the skin friction for the pier that is below that 1.5 meters of soil. So all this part here only. All right, so next is the retaining wall design parameters. So basically you would use these values to design your retaining walls. That is your unit weight of the soil. You've got all your K values. The angle of internal friction was given in the previous table. So that's the angle of internal friction that you use for the retaining walls, 36 degrees. And then on section 8, we've got a site classification. And the purpose of this section is to advise on ground movement due to seasonal moisture change according to AS 2870. So as I said, I imagine you might have a section like that if you are in countries like China, Australia, UK, maybe India, South Africa. I know they have expensive soils as well. China, did I say China? So in this case, we have a site classification of class A, which has little to no ground movement due to seasonal moisture change. If we go back to our second brain, and then we had to this first table, so that is class A, and we've got a characteristic surface movement YS of 0 millimeters, and the type of foundation is most sand and rock, and there's little or no ground movement from moisture chains. This site classification is subject to the foundation preparation recommended by Section 9. Section 9 will give you some recommendations for cut and fill and how you should compact the soil. We would have to do some work in that first meter of fill. And finally, on the appendix, the first thing you would find is the test location. Just bear in mind that this appendix is just a random example. It's not going to match with the report that we just read because we had some client information in here, but the principles are the same. The first image is a footprint of the building with the location of the boreholes and the number of the boreholes. So we've got 1, 2 boreholes for this site. If this site plan was to match the geotechnical report that we just read, we would have 12 spots with the location of the CPTs. And then if we scroll down, we have some examples of the borehole logs. At the top of the page, you always find some general information, and you also find the bore number. So if this is number 1, you can go back to your site plan and you know that that borehole log refers to this location. So if I'm designing part of the building which is close to borehole 1, I would be inclined to have a look at bore number 1 here. So in the first column would be the reference levels. So that one is 52, and then we've got 51, 50, 49, and then on the second column you've got the depth. So you've got the first 500 mil of soil will be fill, and then from 500 to 1.5 meters we've got sandy silty gravel, and then from 1.5 meters to 2 meters we've got a gravelly clay sand, and then from 2 meters to 2.9 meters we have sandstone, and then from there will be siltstone. If this borehole log was for the geotechnical report that we just read, we would have, for the first meter, we would have a sandy fill, and then from 1 meter to 4.5 meters would be our sand. But on this specific borehole log, there's a lot of rock. So on the fourth column, there's a degree of weathering. You can see that the first one is EW, which stands for extremely weathered. Extremely weathered rock is not a solid rock. It has soil properties, but you can still see the texture of the original rock. Sometimes you can easily break it with your hands. If you go on site and pick up some extremely weathered rock, you can even squeeze it and it will crumble in your hand. So it's not like a solid rock. And then we've got another borehole log here. And for this one, we have 500 millimeters of fill. And then from 500 to 1.2 meters, we've got sand. And then the test terminated at 1.2 meters. If there was groundwater on this site, it would be showing on this column. There's a column for water. And then you would probably see a blue color on this area. And there would be a triangle like this, showing the depth where the water was encountered. I hope you enjoyed this video, and I'll see you in the next one.